Oh, that's not what I want. Free body diagrams. Okay, so you have, so these two carts are in contact. Normally, the way that's drawn there, you would think that those would have to be pushing on each other. Well, notice that this 500 Newton force is going to try to pull the 20 kilogram one away from the 10 kilogram one. You know, if nothing's connecting those two things, they're going to separate. Okay, and so it would have been more clear if I would have drawn that with some kind of string or something between them. But that's the idea, is that for them to stay in contact with each other, with the 20 kilogram one being pulled away, they would have to be pulling on each other. But on exams and other questions and stuff, this is the only one that you'll see that doesn't show like some kind of connection between them. Any other homework questions?
Number 6.
Okay, on the free body diagrams? Yeah.
Since they're connected, you add the weight.
Okay. So we're going to do, 100, 500. No, 100, 150, 500, 1,000. Okay. So number 6 in free body diagrams. You have a 100 kilogram one, and it's connected to a 150. And then a 500 Newton force and a 1,000, right? And it says draw free body diagrams of each individual one. So when you do the 100, you have a weight going down of 981 and a force pushing, well, before I do that, let me just do so we know there's this 500 acting over here. The 1,000 isn't acting on this one because it's not on the boundary of that one. It's over on the other one. So we leave that off. There's a pushing force from the ground. I'll call that N100. And then there's a cable connecting them. So that force is parallel to the cable, away from the body. I'll call that T. And so that's it for that one. And then for the 150, you have a weight down of 150 times 9.81, so 1471. And you have the 1,000 on this one, but not the 500. Then you have a pushing force from the ground. I'll call that N150. And then a pulling force parallel to the cable, away from the body. And it's the same cable as this one, so it's T. Okay? And you could also, this is sort of relevant for what we're going to talk about today, you could, if you wanted, decide to treat them both as a single thing and do a free body diagram of the two of them. Then the outline would look something like this. And you would have a weight that's equal to 100 plus 150, so 250 times 9.81 is 2452.5, I think. And then a force pushing up that I'm going to lump. So, there's forces pushing up from the ground on both of them. You can lump them together, and I'll just call it N total.
Can you also do 250 and 250? Or you have to do N?
Oh, sure. Yeah. That's just a variable name. So, you can kind of call it whatever you want. Just be sure that when you're doing these individual ones, you choose different names for those because there's no reason that those are going to be the same. And it turns out if you calculated them, they're different. And then you have the 500 over here. Whoop. And the 1,000 over here. And notice that's it, right? Because now you're going around the boundary that we drew, looking for where the surroundings make contact. Well, the surroundings aren't making contact with that rope, And so there's no, notice that these cable tensions that showed up in the individual free body diagrams are nowhere to be found in the combined free body diagram. And it turns out that's something we're going to take advantage of today. Anybody have any questions about why that is? That can be a little confusing.
What was the question?
Yeah, so notice that on the individual free body diagrams, you see that cable force there. But here, that's internal to our body, And so think about we've done free body diagrams of a person standing there on the ground, right? And we draw the outline of the person and do this stuff. Well, there's a lot of forces going on inside the person. Your heart is beating and all these things are happening, right? But remember that we never dealt with any of the forces going on inside the boundary that we chose. The only contact forces we care about are the forces that the surroundings apply to the boundary of our body. Okay, so that's why this disappears. And not to get too far ahead, because this is what I'm going to be talking about, but if you wrote Newton's second law for one of these, you'd have two unknowns in the x equation. One is going to be that t force, and one is going to be the acceleration component. And so you can't use one equation to solve for two variables, so you're stuck. But if you isolated the whole thing like this, and then you don't have to deal with those t's, now the only variable is a, and you can solve for it. So we're going to take advantage of that thing. Sometimes what you choose to isolate can really affect whether you can do the problem or not. Any other homework questions right now? Okay. So today, we've talked about free body diagrams and using them to write out Newton's second law. Now we're going to talk about some special cases and how to treat these things. So let's call this Newton's second law approaches to some special cases. There's no new physics in any of this that I'm going to tell you. It's just giving you sort of strategies for these that you might not think of, but it turns out they work well. So the first special case that we're going to deal with is objects that are connected. And these are the cases where they have the same acceleration. That's what we're going to do today. Then we're going to talk about rolling and sliding problems. We've already seen some rolling and sliding problems, and we're going to continue to see those. Like this is a rolling problem, right? But we're going to see that there's some things you can do to make your life easier for yourself on problems where things are rolling or sliding along an incline. Okay, so all of the rolling and sliding problems we've done so far and the ones we're going to do today are on horizontal surfaces. Well, what changes if something's rolling up or rolling down a ramp? Okay, so I'll talk about strategies for that. And then the last one is bodies that are connected using pulleys. And this results in the bodies having different accelerations. Okay. So we're going to start out with connected bodies that have the same acceleration. These don't involve pulleys. And so an example of this. So we're going to start with connected bodies that have the same acceleration. And the approach that we're going to use for this is first, we're going to isolate the whole system. And we're going to do that to find the acceleration. And then second, then you go in and isolate individual bodies as needed. Well, it might not have occurred to you on your own that the best approach is to isolate the whole system first, but I already mentioned just a second ago why this is helpful. It gets rid of those contact forces between the bodies, so you can calculate the acceleration. Then you can go deal with those contact forces. So here's the first example I'm going to do. So let's say we have a 5 kilogram cart thing, and it's in contact with a 10 kilogram cart. And there's a 25 Newton force pushing that way. Okay. Are these objects pushing or pulling on each other? Pushing, yeah. I mean, that 25 Newton force, like if they weren't pushing on each other, that 10 kilogram cart would go straight through the boundaries of the 5 kilogram. You see that? And so the 5 kilogram has to push it away to maintain its space, And we want to calculate, so say we want to calculate the force vector on the 5 kilogram that's applied by the 10 kilogram. Okay, this is a really important thing to be able to do for engineering purposes. I mean, if this is, if this is some kind of device or toy or something, and you're trying to figure out what kind of material and how much of that material you need to have in the place where they're in contact, you want to make sure that it's not going to break under this application. And so you need to calculate that contact force to figure out like, okay, 2 millimeters of this kind of plastic are going to work, or maybe we need to go to some kind of metal or thicker or something like that. Okay? So we're just calculating how hard these two things are pushing on each other. All right, so the first step is we're going to isolate the whole system, both things together. And we're going to do that to calculate the acceleration vector. There's a downward weight force. This thing has a total mass of 15 kilograms. So that times 9.81 is 147.15. Then the 25 Newton force acts like this. And then there's a pushing force from the ground. You can call that N or N total or whatever. Just remember that in the next step, when we isolate the individual things, those are going to have different pushing forces on the ground, you know. I'll call this N total. And that's it. Notice that the pushing forces that one applies to the other one doesn't show up. Okay? So now we'll go to Newton's second law. 147.15 is in the negative y direction. So that's the force 0, negative 147.15. The pushing force from the ground is in the positive y direction, so that's 0 N total. The 25 Newton force is in the negative x direction, so that's negative 25, 0. And then this is equal to the mass of this system, 15 kilograms. Notice that that mass is different than that weight, okay? The weight is 9.81 times the mass. And now the last thing we have to do is the acceleration. Is this thing moving along the x-axis or along the y-axis? X, so I'll write this in as A0. And I want you to notice, well, that 25 Newton force horizontally is going to make it accelerate to the left. You see that? It's going to make it accelerate in the negative x direction. But we didn't have to worry about that here. We just had to determine x or y. The sign of that a value is going to come out on its own. Okay. So there's two equations here. The x equation says 0 plus 0 minus 25 is equal to 15a. And the y equation says negative 147.15 plus n total plus 0 is equal to 15 times 0, so 0. Well, we're doing this to calculate the acceleration vector. So this is the acceleration vector right here. The thing we're multiplying to the mass. We don't know it all the way yet because we don't know what that a is, okay? So in order to come up with that vector, the only thing we need to do is find that a, then we can plug it in, okay? So the y equation, it might help us if we were trying to calculate something else. If we were trying to figure out what that pushing force from the ground is, we could use that. But since we're just trying to find the acceleration vector, we'll take this one, okay? But you always have to think about which one gives you the thing you're trying to solve. Okay, so that x equation says negative 25 is equal to 15a. So a is equal to 5/3, 1.6 repeating, This, negative, sorry. That's in meters per second squared. And now plug that a value into this acceleration vector with the dotted line to get the acceleration vector. And so you get this acceleration vector that says negative 1.6 repeating 0 meters per second squared. Or another way you can think of that is a vector in the negative x direction with a magnitude of 1.6 repeating. Any questions about that? So now we've calculated the acceleration that that system is going to undergo based on that 25 Newton force. And since these two are in contact, they're both going to be accelerating that way. Okay? Are we done?
Are we just gonna assume it's negative 25 when it's given to the left?
Yeah. So we already figured out that negative because since it's pointing to the left and our coordinate system, I didn't say this, but we're just using the usual coordinate system. So this 25 is in the negative x direction. And so this is the force vector for it there. Any other questions about this part? So we're not done. We're trying to find the force applied to the 5 by the 10. Okay, so now we're going to do a free body diagram. To the 5 by the 10. So now we're going to do a free body diagram of the 5 kilogram cart. There's a weight force that's 5 times 9.81, so this is 49.05. There's the pushing force from the ground. I'll call that N5 because it's not the same thing as N total from the earlier part. And then there's one other spot where the surroundings make contact with the boundary of the 5. Where's that? So we dealt with the weight force. We dealt with the contact with the ground. If you keep going around the boundary, you get over here on the right to where the 10 makes contact with the boundary. And so we know there's a force there. And it's a pushing force, so it follows the rules of pushing forces. So it's perpendicular to the surface, toward the chosen body, and I'll give it the name R. And that's it. That's a free body diagram. And this vector here, this magnitude R pointing to the left, is the force on the 5 by the 10. So that's what we're trying to figure out. So now go to Newton's second law. We have 0, negative 49.05. N5 is in the positive y direction, so that's 0, N5. R is in the negative x direction, so that's negative R, 0. And this is equal to the mass, 5, times the acceleration vector. What's the acceleration vector? Yep, exactly. So that's why we did the first step. So now we'll just plug our acceleration for the whole thing in for this body. You get two equations from this. The x equation says 0 plus 0 minus r is equal to, I think this is negative 8.3 repeating.
Why is it negative?
Because it's pointed in the negative x direction on the free body diagram. And that's where those components come from. And then the y equation, negative 49.05 plus n5 plus 0 is equal to 5 times 0. Okay, well, this is the force we want. This is the force on the 5 by the 10. We just don't know what R is yet. So we just want to use whatever equation will let us calculate R. So we can plug it in there. So again, what we want is the X equation. And the X equation says negative R is equal to negative 8.3 repeating. So R is equal to positive 8.3 repeating. That has units of newtons. And now to make that a force vector, plug it into this thing with the dotted circle. This is the force vector. And so you get the force vector on the 5 by the 10 is equal to, notice that in that dotted circle, you have a negative times whatever R is. So this comes out to be negative 8.3 repeating, 0 for Y, newtons. Or you could also represent that, since that's in the negative X direction, you could write it as a vector in the negative X direction with a magnitude of 8.3 repeating newtons. So there's a 25 Newton force applied to the 10 kilogram, but not all of that force affects the 5 kilogram. The contact between those two is only 8.3 newtons, okay? So it turns out, like if you're designing this device, whatever it's supposed to do, you could design it just to withstand, say, 10 newtons, you know, something less than 25, and it still wouldn't break. That's what we've calculated here. Any questions about that? Yeah.
So you'll want to use the negative axis?
Direction? Well, we've already figured that out before. Notice that in Newton's second law, we drew the free body diagram, figured out it was pointing to the left because of the rules of pushing. Something to the left is the negative X direction, and so that's how it appeared in Newton's second law. And so you're really just applying that negative sign there. It won't always be negative. Any other questions right now? Okay, so let's do a similar one with pulling. Let's say this one's 10 kilograms and this one's 30 kilograms. And there's a force applied this way of 30 newtons. And let's say we want to calculate what's the force vector applied to the 10 kilogram by the cable. Okay, what do we want to isolate first?
whole body?
Yep, exactly. So free body diagram of the whole thing, both of them together. Altogether, there's a mass of 40 kilograms, so the weight force is 40 times 9.81, so 392.4. Then there's the 30 Newton force here. Then there's a pushing force from the ground. I'll call that N total. And that's it. So now Newton's second law. We have 0, negative 392.4. Plus that N total force is in the positive Y, so this is 0 N total. The 30 is in the positive X direction, so that's positive 30, 0. And that's equal to the mass, 40, times the acceleration vector. Is this thing moving along X or along Y? Yeah. So X, so we're going to write the acceleration vector as A0. The X equation says 0 plus 0 plus 30 is equal to 40A. The Y equation says negative 392.4 plus N total plus 0 is equal to 0. We just want to calculate that A so we can plug it into the acceleration there. So I'm just going to use the X equation. So 30 is equal to 40A. And so A is equal to 0.75 meters per second squared. Now plug this A into the acceleration vector, and you get an acceleration vector of the whole system of positive 0.750. Or in other words, it's pointed in the positive X direction with a magnitude of 0.75. Any questions about that step? That's not what we're looking for. We're looking for the force applied to the 10 kilogram body by the cable. But now we have the acceleration and we can sort of piggyback from that. So now we'll do a free body diagram of the 10 kilogram. There's a weight down of 10 times 9.81. There's a pushing force that I'll call N10 from the ground. And now the only other place the surroundings make contact with the boundary of the 10 is that cable. And that's a pulling force. So that force is parallel to the cable, away from the body. I'll give it the name T. And now we'll go to Newton's second law. So we have 0, negative 98.1, plus 0, positive N10, plus positive T0. It's in the positive x direction. And that's equal to the mass, 10, times the acceleration vector we got from the first step, 0.750. So the x equation says 0 plus t is equal to 7.5. And the y equation says negative 98.1 plus n10 plus 0 is equal to 10 times 0, 0. Well, the force vector we were trying to find is this, which means that what we're trying to solve for is that variable t. Okay, so to find t, we're going to use the x equation again. So this says T is equal to 7.5 newtons. Plug that value into this, and you get that the force on the 10 by the cable is equal to positive 7.5 for x, 0 for y, newtons. And so, like, if you've ever bought fishing line, you have to choose how strong the fishing line is for the fish you're thinking are going to bite. The same thing if you're designing a system like this, you want to make sure that that cable, you don't want to spend extra money making it stronger than you need, but you need to make sure that it's strong enough. So you need to use a cable that's going to be able to withstand at least 7.5 newtons. Okay. Any questions about that? Okay.
Did you see your work on the last one?
Yeah.
Why did it put 65? Oh, that's the acceleration.
Yeah, that's the acceleration we got, and then I multiplied it by 10 there. Okay. All right, let's see. Let's think of some circus people. I didn't realize I was going to have to draw this elephant when I started. Okay, but anyways, here's an elephant. What do elephants look like? They got ears, trunk, something like that. And then over here, we have three people. Okay. And the elephant's going to step down on this teeter-totter and launch this person. Okay. So let's figure out, let's say that this applies an upward force of 5,000 newtons to the bottom person's feet. And let's say the masses here are 100 kilograms. Let's say this is 80 kilograms, and then little guy on top, 50 kilograms. Okay? And we want to know what's the force applied to the feet of the 80 kilogram person. So by the shoulders of the person underneath. Okay? Well, the first thing we're going to do is isolate the whole system to find the acceleration. So that's it. There is a force going down from gravity of, what's that? 230. Can someone calculate that? 230 times 9.81.
2,256.3.
Okay. And then there's a contact force from the ground, well, from the teeter-totter, that's equal to 5,000. We're told that. And there are no other forces. That's a pushing force on the lower person's feet from the teeter-totter. There are no other forces acting on this. So that's a complete free body diagram. And so Newton's second law says 0, negative 2256.3 plus that 5,000 is in the positive y direction, so 0, 5,000. Is equal to the mass, 230, times the acceleration. Is this system of people going to accelerate in the x direction or the y direction? Y, so I'll call this 0a this time. So we have an x equation that says 0 plus 0 is equal to 0. That obviously doesn't help anything. And then the y equation that we're going to use says negative 2256.3 plus 5,000 is equal to 230a. And so that is 2743.7. Yay. Is equal to 230a. Can someone divide that for me?
11.929.
What is it?
11.929.
Oh, 11.93, let's call it. Okay. So now that we should write that as an acceleration vector. So the acceleration vector, plug this into what we already knew was the acceleration vector. We just didn't know the value of it. So this is 0 for x, 11.93 for y. Or if you want to visualize it, it's in the positive y direction with a magnitude of 11.93. And now we will isolate, so we have to isolate an individual person in order to calculate the force applied to the feet of the 80 kilogram person. Okay, what would happen now if we isolated the 80 kilogram person? There would be, okay, so, because that's the first thing you would think of. We're trying to calculate a force on the 80 kilogram person, right? So what if we isolate the 80 kilogram person? All right, well, here's the 80 kilogram person. There's a weight force down of 784.8. Okay. There's a pushing force, the one we're trying to calculate. Here, I'll call this R 100. Well, let's just call it R1. And then there's a pushing force down from the top. I'll call that R2. And so notice in our y equation, we're going to have two variables in our equation. Okay? Hold on. So we have two variables in the y equation, and that means we can't solve it. Okay? So instead, let's do this. Let's isolate the bottom person, calculate the pushing force on the shoulders of the bottom person. Okay? We'll get a value for that. And then we know that the pushing force of the feet, because we're talking about a contact force between the middle feet and the bottom shoulders. Okay? And so the force applied to the middle person is going to have the same magnitude as the force applied to the bottom person. Remember talking about that? It's related to Newton's third law. I sort of mentioned it in passing. So instead, we're going to isolate the 100 kilogram person. So free body diagram of the 100 kilogram person. There's a weight down of 100 times 9.81, 981. There's a pushing force up that we're given is 5,000. And then there's a force R pushing down. Okay? So now we'll go to Newton's second law. We have 0, negative 981. And actually, let me, just to make this clear, this is the bottom person. This is the middle person. And so this downward pushing force is R1. That's the same contact force as this. Okay? So, okay, we got 0, negative 981 plus 0, positive 5,000 plus in the negative y direction 0, negative R1 is equal to the mass, 100, times the acceleration vector, 0, 11.93. The x equation says 0 plus 0 plus 0 is equal to 0, so that doesn't help. The y equation says negative 981 plus 5,000 minus R1 is equal to 1,193. And now we'll solve for R1. So R1 is equal to negative 981 minus 1193 plus 5,000. So R1 is equal to, can someone add those up for me? Two, 826 newtons. Okay. Well, we calculated the R1 from this free body diagram, right? This isolated body. But what we really want is this R1. Okay. And so now that we've figured out that value, we can just calculate this vector from it. And it has to do with the fact that it's contact between the same two bodies, and so that magnitude is going to be the same. And so the force on the 80 by the 100 is equal to 0, 2826 newtons, or an upward force of 2826 newtons. Okay, so in order for this setup to work, like say you're like an evil circus act designer or whatever, and you're just trying to figure out whether this is going to kill people or not, you know what I mean? So the first question is, we already were told that the force on this person's feet is 5,000 newtons. So first of all, can this person continue to stand while supporting a weight of 5,000 newtons? I'm not sure what the answer is, but that's about 1,200 pounds. Can someone with their legs straight support a weight of 1,200 pounds? Maybe someone strong, I don't know. And then the middle person has to be able to support a weight of about 700 pounds in order to do this. Okay? And so now you can use this information to decide whether you're going to try this or not with your elephant, with your own elephant. Any questions about that? Okay. Let's stop there. And next time we'll get into rolling and sliding. Okay, let me give you an outline where we're going, and then we'll be done. So So now we're talking about Newton's second law approaches. To special cases. And there are 3 of these. The first one is objects in contact that have the same acceleration. Next, we're going to do rolling and sliding problems, and we're going to do it for rolling and sliding on surfaces that aren't horizontal. So on inclines, let's say. And then the last one is objects connected by cables and pulleys. And that's going to mean that they have different accelerations. Okay. We're done with this one now. So on Monday, we're going to do rolling and sliding on inclines. Okay, that's all.